Welcome to InnoBuzz Java video tutorial. During this video presentation, we are going to acquire knowledge about one of the most successful programming languages that was created in the 20th century and which became even more popular in the 21st century. I'm going to guide you through all the important core parts of the Java language and going to provide useful knowledge on some more advanced programming tools as well. The following chapters will cover all the basic theoretical knowledge through a suite of slideshow representations with narration, and at the end of each chapter, we will create program codes real-time by using one of the well-known integrated development environments, the NetBeans IDE. To understand the tutorial, there is no prerequisite programming knowledge needed by the audience. Although, as we go on with the chapters, the deep understanding of the previous material can be essential to be able to follow up and use the knowledge. Chapter 1. Introduction to Java and Java architecture. The history of Java started in 1991 at Sun Microsystems, when a bunch of engineers began to work on a research project named Green Project. Their aim was to create a modern programming language which is able to provide support for interactive network televisioning. The name of the new language that was created by the Green team was Oak. The supervisor of the team was James Gosling, who is known as the father of Java. The digital cable television company found this language too advanced for its aims. So the developers had to find a new goal for their work, and this was to create a language that is good for internet development. They gave a new name to this language in 1994, the Java. The main characteristics of the language are easy to learn and to use, object-oriented, platform independent, applicable for network programming, safe remote source execution. The public release date of the Java programming language was May the 27th in 1995. One of the important parts of the language is the applets, which are small web applications running under the web browser. These programs need support from the browser producer companies. Understanding OO approach. To understand the object-oriented paradigm, we have to start with understanding the idea of the concept. These programming languages allow us a very high level of abstraction. If we want to use this kind of modeling, the object will contain the informations that are related and the behaving of the real-world phenomena. So the steps are, we have to use an abstraction on the real-world objects to be able to create our objects in the programs. We will talk about abstraction in the chapter later. Let's see some details about this. The objects contain the data and the operations. The objects belong to classes, and inside them we are going to see that the elements and the fields and the behavior as methods are inside them. Internal properties are protected by information hiding. There is an access mechanism that allows us to reach the protected properties inside the objects. This is going to be called encapsulation. We are going to see it. The classes contain the same type of objects. The classes are going to represent our types in the OO languages. The objects are belonging to the classes as instances. Communication between objects works through messages. Classes express the concepts, objects denote phenomena. This is what we were talking about. The general rules are in the classes, and the objects are going to be concrete instances, and they are going to represent the phenomena. You need to program the classes, not the individual objects. So the basic concept about something that we are going to represent in our program will be written inside the classes. The objects will get all the important related data and behavior that belong to a class. So we don't have to program the objects. We just have to instantiate the classes. Classes are creating an object hierarchy, which makes possible to extend and specialize each other by inheritance. This is a big tree in most of the languages. This is the object hierarchy, and the classes are related to each other as child and parent classes. The child classes extend the parent classes, and this way we can specialize the characteristics of the classes that are upper in this hierarchy. In Java, the top of the hierarchy is the object class, the general object class. Object-oriented and procedural programming. In high schools and universities, the programming lessons usually starts with teaching the procedural manner. In a way, this kind of programming can be called also linear programming. The program lines, in this case, are executed one after the other in a kind of sequential way. The code is executed from the top to the bottom of the file. This is called top-down approach. And the communication between the program parts works through parameters or arguments and return values of functions and global variables as well. So this is the basic about the procedural programming. The object-oriented programming languages are thinking in a different ways. It is not as linear as the procedural way. The code parts, which are executed after each other, can be found in different places in the program text, frequently in different files too. The level of abstraction that is provided by the object-oriented languages is higher. One of the main goals is the reusability. There is an acronym for this principle, DRY. Don't repeat yourself. The main idea of this is to use all the program parts that are already created and never write the same codes again. This means if we write codes that accomplish a task in a general way, that every small pattern of the task is written in a different method, We can reuse these program components whenever we want to solve problems that are similar to each other. And also, if we write again the same program parts, then we should know that we should have reused them, and we should have made even smaller patterns from them, so we could have reused them. The object-oriented programming involves the bottom-up approach. This is the opposite of the top-down way. The main idea of this is to group together program components to form bigger units. It starts with the fields and the methods that form the objects. After it, there are the objects that are associated with each other, and they belong to a bigger set, the packages. The packages are arranged in folders, libraries, and the entire system stands out of these bigger units. The objects communicate via interfaces in object-oriented programming. There are communicating methods and functions that allow us to reach the inner fields of the classes. And this is a way communication that is provided by object-oriented programming. We can communicate with the corresponding objects through well-standardized interface structure. What is an object? We have already talked about it, we have already seen it in the previous slides. This time I'm going to give a short description, a short sentence, a short definition of it. We could say that an object is an instance of a class. In the object-oriented programming paradigm, the data is the most important factor. We can store, reach, manipulate the data through the objects. The objects are grouped into classes. The classes contain the data as fields and the functions and methods as behavior. The methods are a set of activities that belong together to be able to fulfill some kind of requirement in a general manner. The objects are the instances of the classes with the specified concrete data that makes every object unique. The general characteristics of the classes are all applied on the objects, and the default data is also available. So we can see the classes as abstract recipes, formulas for creating the concrete objects with unique data settings. Let's talk about the most important features of the objects. The state and behavior. The concrete objects that are instances of the classes always have a state, which is defined by the data that it contains at the moment in its fields. The behaviors of the objects are determined by its methods. The methods of the classes perform specific operations and tasks. The methods can be reached, called through the object instances. Every object instance is unique and can be differentiated from all the other objects by its identity. The identity is realized in most cases by a reference to the corresponding object. The references are often memory addresses technically. We can reach the objects through a reference which identifies it like a pointer that has a specific type. It is also possible that more than one reference points to the same object. Responsibility. Every object has to be responsible for itself. In a more precise way, we could say that the objects have to have the fields and the behaviors that are essential to be able to perform all the functions that they are expected to do. There are cases when the corresponding object cannot do the specified task, but in these cases, it has to be responsible for knowing how to call the service or how to find it. 4 major and 3 minor OO pillars. In the previous slides, we have already talked about some concepts in Java language and in other object-oriented languages. We are going to see these pillars in details now. First, I'm just going to name them here, and we are going to see them in the next 7 slides. We have seen the abstraction, which is one of the most important major pillars. We are going to see the encapsulation. We have mentioned the inheritance. We will talk about the polymorphism. These were the 4 major, and the following are the 3 minor pillars. The strong typecasting, the persistence, and the concurrency. Let's go now in details about these concepts. Abstraction. In the previous slides, we have already talked about abstraction. We could say that abstraction is simplifying the complex reality by some kind of modeling. To understand this, in my point of view, the easiest way to start is to view it from a different point and start from the philosophical way of the abstraction. In philosophy, Plato created a theory about the ideas. In this theory, there is a world of ideas where everything which is in the real world has some kind of abstract idea. I'm going to show it with an example. Everyone knows what a chair is. The chair in our head, in our way of thinking, is some kind of abstract thing. We call chair everything that we can sit on or something. This is a short definition for the chair. But in the real world, we cannot find general chairs. We can only find concrete chairs. We can find a chair with 3 legs, which is good for the shoemakers, for example. We can find another chair with 4 legs, which is good for eating our breakfast, or we can find a special leg chair for playing the piano, for example. So these are the concrete chairs, but in general, everyone knows what a chair is. And this is because we have an abstract definition in our heads about the chairs. And this is the abstraction when we create program. We have to think of the real world and have to get the parts, the elements of the real world that we need to implement, that we need to know about them. And the others are not really important. If we are talking about abstraction from the programming point of view, we can say that it is a process when we want to create a simplified model of the reality, and we consider only the most important features and attributes as parts of our mapping. In object-oriented languages, the abstraction means that we create the fields and the behaviors, the methods, which can represent the system. The communication with the model can be done through an interface. So we can see it like this. We have got a part of the reality, and this is a complex system, and inside our model we only use the important features. In programming, to be able to create this kind of abstraction in Java, we are going to create abstract classes and interfaces and an inheritance structure. And through this, can we provide this high level of abstraction. The main point is that these kind of classes are not giving the implementation. They are not telling the objects and the classes how to do something. They are just telling in general what to do. So they are going to tell that some methods in some ways have to be implemented. The concrete implementation of the methods is up to the classes that implement these interfaces. And it is also important that these abstract classes and interfaces also can be used as types in our programs. We are going to see that in the practical part, and we are going to write programs on using this kind of general feature of Java, which provides the abstraction. Encapsulation. This word is created from the word capsule, which is used in pharmacy, for example, to put the medicines into a special holder to preserve the content. The basic meaning of encapsulation is hiding the information about the objects inside the classes so that they can be reached by only through an interface which has predefined access rules. This way, the implementation of the behaviors can be separated from the interface, which through can we reach the model. Technically, it can be done by declaring restricted, private access to the fields and providing change possibilities to them through public methods. This is called the access mechanism. This way we can create more robust and reliable codes. We can modify our code in a safe way, and the programs that are already using our program codes, the codes that are referring to our codes, that the programs that are calling our methods, will not be harmed. They will work as expected, so they won't crash or something. This is important because when we create programs and other programmers start to use the methods or the possibilities that we created, program libraries, for example, or program library packages, then we have to be careful with modifying it. For example, inside a company, there are some rules. When we create the programs, others can refer to it. They can call our methods, and the encapsulation also provides this possibility that we can change our code in a safe way. Inheritance. In object-oriented languages, the classes are associated with each other in a hierarchy. The classes that are in the upper levels of this hierarchy are the superclasses. And the classes that extend them, that are in a lower level of this hierarchy, are called the subclasses. This association is frequently described as a parent-child relation. The extender or subclasses inherit the fields and the methods of the superclass by default, but there is also a way to change, to specialize the features of the parent in the child classes. This way, all the subclasses that belong to a superclass can be different and can have their own behavior. Basically, we can talk about two major types of inheritance, the single and the multiple one. The single inheritance covers the situation when a child class can have one parent class. In other words, the subclasses can extend only one superclass. The multiple inheritance has different rules. In this kind of inheritance, the child classes can have more parents, which can be technically done by extending more than one superclass in a subclass. In Java, generally, there is a single inheritance when we consider the class structure, although there is a way to achieve multiple inheritance when implementing interfaces. So the rule is that a class can extend one superclass, only one, but can implement many interfaces. This can be called partial multiple inheritance. When we extend classes, there is a possibility to override the methods and the constructors of the superclass. This means that we are going to create the same methods with the same signature, but a different implementation, different code. We are going to talk about it more detailed in the next slide. In Java language, the inheritance structure, the class structure, looks like a tree. The root of this tree is the class object. It is a general class that is the first parent of every class. So all the classes belong to the object in some way. Some of them is directly extends from the object. By default, if we don't specify the parent of our class, it is going to be the child of the object class. Of course, we can specify the parent class by extends, but the root of the structure is the object, so everything comes from it. Polymorphism. In this slide, we are going to see what the possibilities are in the extender classes for changing the behaviors of the superclass. The ways of polymorphism lets us to do it. Polymorphism means that some programming elements, like methods and constructors, can be found with different implementations inside the same code in the inheritance hierarchy. The name and the arguments are the same, but the code is different. The advantage of applying this pillar is flexibility, simpler codes, less efforts to change the program, and the possibility that depending on the type of the object instance that we call, a method on the corresponding specified codes will be executed. If we talk about the polymorphism in Java language, we can realize it technically by extending classes or implementing interfaces. This way, the instances of the subclasses can be used in any place where the superclass or superinterface instances can be used. There are two major types of polymorphism, the static and the dynamic one. The static polymorphism is realized by method overloading. In this case, the method signatures are different from each other, and the method binding and the calling of the methods happens in compile time. This can be done because the compiler is able to choose from the different method signatures the one which is adequate. The dynamic polymorphism is realized by overriding. The signatures of the overridden methods and constructors are the same, and the method definition can be done in runtime. The class interpreter chooses between the possible method or constructor versions by checking the object type that the call was written on. For example, in one method there is a general class or an interface specified as a formal input parameter. But during runtime, there is an actual parameter of one of the subclasses or one of the implementing interfaces of the corresponding class. And in this situation, the overridden specified method inside the subclass will be called. Strong typecasting. The programming languages can be categorized into strong typing and weak typing ones. The difference between these categories is in the rules which specify the possibilities to use different type of variables or objects in one operation. If the corresponding language allows the intermixing of the types in one operation, then it is weak typing. If the language has more strict rules for this, it is called strong typed one. The type system can this way allow us to create safer codes that are not going to crash with errors or exceptions during compile or runtime. This means that there is a kind of guarantee for the behavior of our program in this manner. For example, in strong typing languages, it is not allowed to use the most basic mathematical operations like adding or multiplicating on different types such as int, float, char, or the string types. The strengths of the restrictions about typing that the programming languages use form a very wide range. So there are more and less strict languages if we are talking about the typing. In a strong typing language, the class instances can have fixed or invariable type, which means that it is not possible to change the object's class over the life cycle of it. Talking about Java, we can say it is a strong typing language, but compared to other strong typing languages, it doesn't have the strictest type rules. The type system is supervised by the JVM, the Java Virtual Machine, in a dynamic manner. What happens if we have a strong typing language and we want to intermix the types when using an operation, although it is not allowed? To be able to do this, we have to apply a typecasting on the variable, which basically means an explicit conversion of the corresponding variable or object to another type. This is the changing of the classification, which in some cases also indicates a new kind of representation. This happens, for example, when we cast an integer to a float. Persistence in the informatics is a general concept that describes the situation when a data is able to survive the program that has created it. In other, simpler words, you could say that we are storing or backupping some kind of data for further use. In Java, there are different ways to perform some kind of persistence. For example, we can write out our data into a file. But the most frequent way to do this task is to store in a database, especially in a relational database. There is a very wide range of the data types that we can store in databases. Primitive and complex object types and arrays and images, so almost everything. In the world of network programming, for example, it is crucial to be able to store lots of information and to be able to reach it fast. So in general, we have to store our objects in databases and our data. Manipulating databases from our Java code can be done in several ways. One of the best supported and most widely used tools for this is the Java Persistence API. This is a Java programming language framework that was specially created for managing relational databases. The API can be found in the javax.persistence package. There is a query language built for database access, the Java Persistent Query Language. By using this language, we can make queries to our relational database. These queries are similar to SQL queries. There is also a possibility to connect to databases from our Java programs through an ODBC or a JDBC connection. We are going to discuss this in chapter 14. Concurrency. One of the most important features in most of the object-oriented programming languages, and especially in Java, is the multi-threading, when different program parts can run at the same time, parallelly. The concurrency covers the ability of a programming language to support this asynchronous task execution in a highly organized way. The main goal of concurrency is to be able to solve problems faster, and to achieve this, the problems have to be sliced into smaller parts that can run parallel. So we have to dissolve them into subtasks that we can run parallelly. As the number of multi-core CPUs is increasing, the possibility of creating real hardware-supported concurrency is also gaining. Note that if there is only one processor, the multitasking can be done by sharing the processor time between the processes. So the real concurrency can work on the multi-core CPUs. Let us talk about the processes and the threads now. It can be crucial to be able to tell the difference. Both processes and threads are some kind of standalone sequences of execution. The major difference is that threads run in a shared memory space, while processes run in separate memory spaces. The processes are generally bigger units that are started with a primary thread, but additional threads can be created from them. The threads are inside the processes, and their execution can be started and handled from there. The threads in a process are sharing the same virtual address space, while the process has its own one. We are going to meet the Java threads and the multithreading in the 10th and 11th chapter. Features of Java. Java is a modern programming language with a syntax that is similar to C and C++. The learning of Java is very easy if we understand the major idea of the object-oriented paradigm. We can write short, easy readable codes with lots of reusable parts. We have seen them and we have talked about the object-oriented paradigm a lot. The Java, in some way, is both compiled and interpreted language. This gives the possibility of being portable to any system. The execution of a Java code stands out of two phases. One is compiling the source by the Java compiler, which ends in a Java bytecode file. The next phase is to interpret the bytecode by the JVM, and this can be done at any platform the same way. This is the platform independency. With Java, we can create robust codes. Java gives the possibility of the early checking for errors, which means that the compiler detects many possible errors already in compile time. The JVM provides also the runtime checking, which is the dynamic way of error detecting. We have talked about this strong typing as well. This feature also provides a high level of code security. The fact that in Java there is only single inheritance, considering the class structure, is also an important advantage that helps to avoid some possible errors, thus leads to creating safer, robust codes. One of the most important major features of Java language is the possibility of making high-performance multi-threaded programs. With the concurrent programs, we can easily create interactive applications, and we can prevent the code from locking up. Using threads can be especially essential when writing network-related programs. We have seen that the number one goal of the creators of Java was to make a programming language that is able to answer to the problems of network programming. With Java, we can construct virus-free, safe internet applications. The small applications called applets that are running client-side are one of the most popular Java specialties. Java is also very frequently used to create server-side programs nowadays. Java architecture. When we are creating programs in Java language, we are creating a Java file, a text file which has the Java extension. And after we save it, we want our program to be executed, of course, and we want to run our program. Well, the Java architecture is built on providing the ability to run this application that we have created. But there are several steps for being able to run a file. First, there's the Java compiler, which makes from our Java file a class file. Then the class loader is going to load our class, which is already a bytecode. And then the bytecode verifier checks for security reasons. And the Java virtual machine is going to actually run the file. Java compiler. After we have created our program in Java language, we save it with the Java extension. And now we want to execute it. The first step that we have to take when we want to run our Java program code is to compile it. The Java compiler creates a special bytecode from our Java source files which have the class extension. These are the platform-neutral Java bytecodes which can be run on different systems. There are different possibilities for the programmers to make the compilation of their Java files. The first that we mention is the Javas inside the JDK. This can be run from console windows. There is also the GNU compiler, Java compiler, the GCJ. The codes compiled by this have better performance at startup. There are also built-in compilers in program text editors or in integrated development environments such as Eclipse or NetBeans. During the process of compilation, there can be different kinds of problems happening. These are the compilation errors. The most common thing here is the syntactical error. These kind of problems indicate that the source file cannot be compiled. There are also some smaller problems, some smaller errors that are not serious enough to make the compilation end without output. These are the warnings. So if we have warnings, the class file is created. The class loader is an important part of the JVM. This is responsible for loading the classes dynamically into the Java virtual machine. The classes are loaded only if there is a request for them. The JVM does not have information about the file system. The class loader does this job for it. All Java programs start with the public static void main method with string arguments. The other classes that are referenced by their name in our programs are loaded one after the other by the class loader during runtime. In all JVMs, we can find an embedded class loader, which is called the primordial class loader. This is important because, as we have mentioned, all the classes are loaded from another running class by a class loader, which is also a class, there has to be a first class loader that starts this chain. This is the primordial class loader. It is written in a native language, for example in C. The primordial loader has access to a specific set of so-called trusted classes. These are the classes that can be run by the JVM without going through the process of verification that we are going to talk about in the next slide. All the most essential preparations before loading our applications is done by the primordial class loader, like searching the class path and the jar files, for example. There is also a possibility to create user-defined class loaders. These lets us to dynamically extend the Java application at runtime. So when our application is running, it is possible to load the extra classes that we need for our program. This is an advanced and even more dynamical tool for programmers. The bytecode verifier is a part of the JVM that runs after the class loader before the interpretation of the class file. The trusted classes are not verified by this mechanism, as we have just mentioned. The others are checked for some typical problems that are easier and faster to find before the execution of the class file in runtime. So the bytecode verifier will save us time. Let's see some of the typical problems. The illegal object reference. The use of an object in a place where another object type should be used. Illegal parameters. For example, when calling a method or a constructor with illegal arguments. Stack overflow and underflow. The call stack works similar to other stacks, just like in programming. There are the operands that are put in and popped out. The work of this verifier can be described shortly, like verifying, checking whether the number of puts into the stack isn't too much for the stack or if it is less than the pops. So if we want to pop out more than we have put in, it is an underflow. The illegal typecast. When we want to use an object type when it is not allowed and there is no possibility to make a typecast there. Breaking the access mechanism rules. Calling an object from a place at the program where it is not allowed to be seen by the object access mechanism. So these are the things that can be checked by the bytecode verifier. And the workflow of the bytecode verifier looks like this. First, it checks the class files syntactically, checks the relationships of the bytecode class context, then verifies the control flow statements, and then checks the outer references of the file. The Java virtual machine stands out of different parts that make it able to execute the bytecodes that are created from our Java source files. We have seen the class loader, and the bytecode verifier so far. Now let's talk about the interpreter part of the GVM. There is a so-called GVM specification that sets up the rules for how to interpret the instructions that are parts of our program in a way that it is possible for the processor to execute them. One of the most important features of the GVM is that it can do the interpretation of the class files in the same way on every platform. So the same class file can be run the same way on all platforms. The GVM is not a physical machine, but more like an emulator program in the memory of the computer, which is an interface between the bytecode and the computer. The most important parts of the GVM are the following. The set of registers. The state of the machine is stored in them, and this state is changed after the execution of every line. A stack, an operand stack, which provides the arguments of the methods and the operation. And this stands for the return values as well. An execution environment. This works with the stack and provides the dynamic linking, the return values of the methods and the exceptions. Garbage collection heap. The other name of this is memory allocation pool. This provides the memory that it is needed for the instances, for the objects. The constant pool. This is created at compile time, as the constants in the programs do not change their values. The method storage area. This has the compiled bytecode presentation of the methods. And there is an instruction set that provides the instructions to be able to use all the previously mentioned components. The bytecode instructions that are used by the GVM are similar to assembler codes.